my name is Ryan, and today we are going to learn about how Kruskal algorithm works. So essentially, Kruskal is one of the minimum spanning tree algorithms that is commonly used alongside prim. So how does Kruskal works essentially? Well, here's the first to the point. There are examples online, but here's the short picture. Here's my interpretation of it. So first, we have let's say we have a what's called graph, non-directed graph, let's say. And then what we do, in short, what Kruskal does, well, check it online if you want to get a full description of it. What Kruskal does is that they would sort the graphs, the edges, and then use disjoint sets to prevent loop. So loop is what happens when this is an undirected undirected graph, which means that there are possible loop scenarios. For this loop happens when a visited edge is revisited again. Let me rephrase that. A visited edge has been is revisited. So that's what is loop. And then we use disjoint sets to prevent such. The implementation will be a little bit simpler in the coding, but yeah, as long as you get it, it's fine. So the last one is actually this is the steps. These are the main steps. All right. Now what we do is let's say we prepare two sets. Right? We prepare two sets. Let's say source. We connect them with index. Let's say we want to have 6 nodes, maybe 8, yeah, maybe 6. I'm not gonna use user input here, right? We're going to put, actually, yeah, maybe I should use user input. Source, destination, of course. This is a let's go with and wait. Let's just put it in a simple example using similar arrays that is connected to an index. Let's use scanf. Hold on, let me prepare the stuff that we need. Now this simply put, we just loop it and fill it, right? This is not the AI level Kruskal implementation, but this is just an implementation based on implementation in procedural programming. This is not AI level. Let's say source, destination, and wait. Scan each of them and we will put an input. That will be our source material. Now, next, what do? We have a node of undirected graph. We have a node of undirected graph. And then use any sorting algorithm to sort each of the edges. Sort the weight. In this case, I might want to use selection sort because it's simpler. Let's say we compared based on weight. Oops. Again, optimization. Optimization is necessary to make your program run faster. Double loop, do not forget, because it's important. Record it. Forgot the whole stuff. I'm used to code in PHP language. We don't need to. You just need to declare $. Again, if you want to learn about selection sort, you can check my previous video about 3 basic sorting algorithms: bubble, selection, and insertion. I'm using selection because it's more simpler in terms of how it works. Although not fast, it's just simpler. Okay, we just need to record the I. We just need to record the index. Now don't forget, we have to switch out other things too, such as the source and destination. All you need to do is to just copy paste it, but keep the index connected by doing the same thing. I'm gonna prepare a printing method here. Let's see if it's sorted out. Oh, my bad. It's actually not weight I, but weight index. Ugh. Alright, there we go. This is a selection sort, but you see it's more like some you know, it's more neat, I guess. Let's start 1, 2, 6, 5, 2, 2. Hold on. I think I didn't press something. 1, 2, 5, 2, 3. I forgot. I only scanned for 1. Did I? Yeah, wait. I didn't press N here because it's important. Never forget this, guys. You always need to oh, right. Okay, there we go. And always press N for pointers. One more. Okay, let's. I forgot the /n over there. But yeah, as you can see, it's sorted out. Source, destination, weight. Oh, sorry, my bad. There. Right, this is the first step of Kruskal. You need to sort each of the indexes. In an ascending order. That's also important. Sorry. Yeah, apparently I didn't. Yeah, I forgot. Okay, ascending order. See, now we got this. We got an sorted array. Assuming. Now what we do here? What we do here is we will use disjoint sets. What is disjoint sets? Essentially, in short, it's a way. In short, it's like you compare you check for each source and destination whether or not they exist within the sets. If they have existed somehow, we will remove them. Let's create a function to do such. This function will check two things: the array, the source. No, we don't really need to do that. And then void sets. I just call it sets. And then int the number. Now we will check whether or not we assume it's 6. It's always 6, right? This is the simplest implementation of the disjoint sets. No, it's not fully implemented yet. It's half, only like halfway. This means that number exists, which is no, refuse. Otherwise, number does not exist. Yes, accept. That's the point. That's the disjoint set for you. Now we will try to compare each of these sets. This is assuming that each of them has already been in ascending order, so we'll use the function disjoint. No, for 6 times. First we'll check on the source. We'll check on the sets. So we check on the sets, right? We input each of them. We check on the source and both on the source and the destination. This is first we check on the source. No, we have to check both. So yeah, first we check sets source. I guess I can just call this source and dest. So we're checking 2 at the same time. One thing to note that the destination cannot exist. The source and the destination cannot, even though, like, if let's say we have a number and then it exists whether or not if it's in the source or in the destination set. No, reject it no matter what. Reject it. Don't accept it. First we check for the source, then we check for the destination. Again, if we do this again, if source I has a number on it, then return 0, return 1. This just simply just change it to destination. Now in here, what do we do? What do we do is we check each source and destination with this source I. No, wait, disjoint. Wait, what's the function name again? Yeah, disjoint. I didn't save it. Disjoint. So we will check the source of I, dest of I. Now what do we put on the number though? Well, simply put, this is the checking this. No, this is checking for both source and destination. I wish I can do dynamic implementation of stuff. I can show you the size of stuff, but whatever. Never mind that. In my previous one I used size of, but it doesn't work in this thing. I don't know why. But here we go. So first we check for source I. No. Yeah. Here. So we check for final end final source. This is, let's just give it a huge whopping size, even though it's a waste of memory, but whatever. Final dest and final weight. Essentially what this does is, after we do this join, perform a disjoint sets, we do this, we apply disjoint sets into this thing, we will just, you know, add it to final list, final weight. Now what do we do here? Final source, final dest, final weight. What do we do here? Okay, we're gonna just, once they return, if disjoint returns a 1, then we add it. Let's just say this is like index int f index. Yeah, and maybe, yeah, wait. Final source equals to final source of f index equals to source of I. Then we just add each of them. Final source, final dest, and final. Oh, one more thing. We should check it from the final source and destination, because this is the one that we're going to compare. Final source, final dest. Source, final dest, and weight. This is the key. Final source, final dest, final weight. First the source. Compare source, this abyss. Yeah. So we compare the first source, the source, and the final source, final dest. We compare it. We see whether or not the source and destination is there. Alright, there we go. I see now. So now, simply put, we don't need that loop actually. We only need the first this thing. We need the first loop. Essentially, we are going to source. This shows displays what we compared with the list. First, we compare the source. Big, small, just for differentiation. Source, dest, so each iteration we would compare each of them, set, and then what do we do here? Well, what do we do here is just we don't need this. We can just use I, honestly, because it's definitely going to be like that. Yes. And then after the source and destination is done, you add the 0 and then final source, final destination, and wait. And then you would remove it. Otherwise, don't add it. And then I think that's it for Kruskal. It's not that complex. Wait, what is this? Oh, right. This doesn't belong to anything. Right. Let's see if it works. This is Kruskal in a very, very basic implementation, by the way. Don't take this for granted, because Kruskal AI is way much more different. Way much more. It's like different. It's so different. It's just that final destination, final wait. Let's see it. Oh, final destination. Oh, it was final dest. I'm sorry. Void to point. Right. Ah, right. I forgot. There. Let's try it. 1, 2, 5. 2, 1, 2, 3, 4. This is yeah, wait. 3, 4, 5. 2, 4, 2. Let's see. 3, 4. 3, what 4 is like that? 1, 4, 1. 2, 5, 6. Wait, hold on. Did I print it out again? Yes, I did. No, I don't think that's the issue. Bug fixing, very important part of programming. So it is in the descending order, right? We'll just make it descending. Did I press use N? No, I didn't. Yeah, I know what to know. I know the issue. The issue is in this sorting algorithm, I guess. Not much to it. Right. Right. Yeah. That's it. I want to see. Wait. Before that, okay, we did it. 1 2 5 4 2 3 1 4 5 6 1 3 2 1 4 1 2 5 2. Strangely, it's not sorted in based on. Obviously, when the I'm sorry. Dude, I pointed at the wrong index. I think that's the issue. 1 3 2 2 5 1 3 4 maybe 2 no 3 4 3 3 4 4 5 2 1 4 1. Okay, otherwise we just filled with 0. I think that's a fair comparison. Zeros meaning that they're not going to be taken, because at that time it plays like memory. It plays empty memory, which means we haven't assigned anything to it yet. 1 2 5 2 3 2 maybe 1 3 4 2 4 2 4 3 3 4 4 1 4 1. So in here it says that only the minimum spanning tree that we got is 1 4 1 and 2 2. Is there even the 2 2 2? I think there was, but it didn't. Yeah, wait. I think I did something wrong in the assigning. Let me see. Yeah, I think I did something wrong in the assigning. I don't think this is correct. It should be destination. My bad. Little mistakes. Little mistakes. Let's try that again. Nutriforce already there. So yeah, the minimums, the what's called the unique one is, let's see if it's sorted well. 2 4 4 and 3 5 5. That's the one that is being taken. 1 2. Wait, I want to see. Wait, is it sorted or is it seriously sorted? Hold on, I really want to see. Sorry for this is called debugging. This is the debugging phase. Every programmer must face this. Let's see. yeah, so it's not sorted as you can see. If it's not sorted, it's gonna screw up. So it has to be sorted somehow. What's the issue here? Requires precision to get this done. I think it's in here. Alright, I want to see my algorithm a bit. No, we don't really need that. Index I. Yeah, seems alright. Nothing too odd. Oops, sorry. Wait, index temp. Yeah, maybe I screwed up a bit here. In here, maybe. So the weight. Index is equals to I. So what's the result of the sort? Let's try that. That's a bit weird because this is in descending. Let's try somehow when I do this instead of ascending it, it just goes to, it's just weird. It just acts weird. It is alright. That's let's see how I switch it. I see now. I haven't switched the select. That's why. Wait, it's actually it is necessary actually. This is just to point it out. This should be it. Man, sorting algorithms can really be a hassle. Be a bother. Really a bugger, honestly. Okay, there we go. As you can see here, we deliberately reject 342 in here. It becomes 0, right? Why? Because 342, according to the laws of graph, to the rules of graph, undirected graph, you cannot have a loop in your minimum spanning tree. So from 241, because 34 indicates a loop, a possible loop. So 241, 453, and 124 is the result. Well, okay, let's just go through it one by one. 241, 342, 453, and why is 234 rejected? Because 2 is already in here, because it's already there technically, so we cannot accept it. And why is 145 rejected? Because 1 is already here, and 4 is already there, and 4 is already here as well, so it's definitely going to get rejected. Let's compare it with I also made a Kruskal algorithm. This is a more like sophisticated one, I guess. Not really, it's just long as hell, because I'm using bubble sort and stuff. This is like a more dynamic version of like Kruskal. Let's try it out with the same test case. This is this is more sophisticated than the previous one. This is just an example. Input number of nodes, let's see, 6. Input source dest weight 124. Two, three, four, 1, 2, 4, 5. 1, 4, 5. 3, 4, 2, 2, 4, 1. 2, 4, 1, I think. Yep. And then the last but not least is 453. Let's see how it works. Strangely it puts 341 in, which means I might be mistaken, because I think I don't quite remember, it's like 3 semesters away now, but I think the law that I think the issue is you don't if one of them is correct, let's just say this. So essentially, if one of them is not in there, return 0. Alright, this is the way. So yeah, I think that's the issue here. The issue here is that it's not strictly both of them cannot be there, but if one of them is still unique, let's say, they will be included. So let's change a bit of the logic, a bit. So we're prioritizing this. We'll use the verdict algorithm. Verdict is 0. Verdict is essentially 0. Now we copy paste this. Verdict summon 1. Verdict equals to 1. Oops. So verdict is essentially what happens when a node is found on the disjoint sets and the sets. No, we don't need that again. Verdict plus summon set. Let's just do this a bit. Add verdict to 1 again, and then return the verdict. If verdict is not less than 2, which means if one of them is unique, then we'll add it. Because I'm referring to this one, the one I made over here, because this one first is more sophisticated. Look at that. And the second one is because it has been checked. My friends actually checked on this on the source code and do it a few test cases, and it's correct according to their according to their validation, according to their when they check it, it's correct. So let's just use the same test case over again. 1, 2, 4, 1, 2, 4, 2, 3, 4, 1, 4, 5, 3, 4, 2, 2 4 1 4 5 3. I think it's a bit different. Yeah, it's a bit different. They might be restricted on the source a bit. Yeah, I think it appears that they are more restrictive towards the source. So maybe we should do this. Because I think that's the way it works. It appears that, yeah, it appears that so who didn't made it? 453 didn't make. No, 453 made it. 124 made it. 145 didn't made it. Yeah, 145 didn't made it. Why? First of all, it's the last one. I don't think 145 made it either in here. 234 didn't made it too, huh? So yeah, it appears that they're more restrictive towards the what's it called, the the source. Let's try it again. So it appears that they are more restrictive. It appears that this joint sets the law of, I kind of forgot the way that what's it called, the thing is, you cannot make it loop. I think the source is the most restricted there. Oh, sorry. Let's try a different test case too. No, 24 is already there. So yeah, according to this, only 3 made it. Let's see what's according to my correct one. There are 6 nodes. This is the one I know that this is not. I didn't copy this from any internet or whatever. I tried to make it my own. Tried to make my own implementation. Like what? That was me in like the 3rd semester, I think, or the 2nd semester, or 2nd to 3rd. I kind of forgot, man. I think it was yeah. I think it was like 2nd to 3rd semester. I made the code at 2nd, 3rd, so I kind of forgot how to do it. But whatever. Let's just move on. Alright, there we go. 141, 452, and 233. And the rest is history. So yeah. Apparently they are more strict towards the source. I think. They are more strict towards the source. Because with the source, that means with the source, that means you can't do much again. What's called? Let me see here. They are more strict towards the source. I think it's a bit different than what I did here. Yeah, it's a bit different in here. I'm reviewing my own code. It's a bit different here too. I use decrement system where it's like 2 1 0 2 1 0 0 again, and then yeah, pretty much like that. When it's more than 0, you just put it in. Otherwise, don't put it in. Otherwise don't put it in. Put it in if you think it's better. It's more than 0. Let's try another different test case, just to validate it. Let's try 2, 4, 5. Man, oops, this is not the one. This is dynamic programming. Oops, this one. 2, 4, 5, 2, 3, 3, 1, 4, 1, 2, 3, 1, 2, 2, 2, 2, 5, 2, 3, 4, 3, 4, 5, 2, 4, 5, 4. Alright, it says here that 4 notes are taken. Let's see the next one. There we go. We have 6 notes. 2, 4, 5, 2, 3, 3, 1, 4, 1, 2, 5, 2, 3, 4, 3, 4, 5, 4. That's a bit strange. It says here it should be 5 notes that's taken. Okay, so second test case doesn't work. Well, it says 1, 4, 1, 2, 5, 2, 2, 3, 3. 2, 3, 3 is somehow taken. Okay, we're gonna make a stand here. I don't think the verdict is as strict. I thought it would be strict, but verdict it should be 1 here. Add by 1. Add by, and then do 2. And then do that, and then that should be it. Supposedly this is the most simpler one. Yeah. Let's try a different test case again. So according to this, there will be 4 notes that are taken. Let's see the second one. We'll compare. Yeah, 4 notes again. 4, 5, 2, 1, 2, 3. Yeah, it's although this one's a bit not in order because I describe it differently. 4, 5, 2, 1, 5, 3, 1, 2, 3, and 2, 3, 4. 2, 4, 5 is somewhat taken. I think there's one rule that I'm missing here. 1, 5, 3 is not taken though. I wonder why. Wait, is this like in the previous version or something? Let me see. It is like that. If verdict is less than 2, that means yeah that. Otherwise, just add it 0. Did I make a mistake or something? Weird. Yeah, this takes a while to debug, honestly. Sometimes depends on your skills. Hold on. Debugging takes a while, like real life programming. Okay, the one's not taken is 141, 342, 233, 124, and that, and so the fifth one's not taken. Alright, according to this one. How about this one? Okay, we have 6 notes. According to this, 1, 2, 3, 4, 5. Yeah, 5 notes are taken. Now this is correct. 141, 342, 233, 245, and 456. And there are only, so yeah, the last note is not taken. Sometimes there's like maybe the bug of def C++ that didn't execute. It's sometimes that's why I don't really like def C++, I guess. Let's try on another test case, and then I'm happy, because yeah, you always try to save it first, and then just okay, it's still recording. Let's try 4, 5, 6, 2, 3, 4, 2, 4, 4, 1, 4, 5, 1, 3, 2, 1, 2, 3. Okay, that one's a bit nice, a neat test case. Let's try the other one. But no, 6, 4, 5, 6, 2, 3, 4, 2, 4, 4, 1, 4, 5, 1, 3, 2, 1, 2, 3. Alright. Takes 5 notes instead of 4. That's a bit strange. I don't know why. One, 3, 2 is taken. 1, 2, 3 is taken. 2, 3, 2, 4, 4. 4, 5, 6 taken all the time. Somehow this one's taken too. I guess that makes sense. I thought I already changed the verdict so that it's okay to have like 1, 0, 1, 2. If it's less than 2, then take it. Oh, it is. It's technically. Okay, let's try to debug here. You know what? Let's try to debug here. So the order is like this, right? The order is like this: 2, 3, 4, and 2, 4, 4 in here. 2, 4, 4 is actually not. No, 2, 4, 4 is taken. But 2, 3, 4 somewhere is not taken. I already said that this thing, it should be like this. It should be like this, honestly. I mean 0, 1, 2, and then the verdict should be, if it's less than 2, delete it, don't include it. Otherwise make it 0. This is kind of weird. Final source finds death. It should technically work like that. Similarly, it should work similarly, but it's just that I don't know why. What the hell? S2, 3, 4. No, if both exist. Wait, that means it's, yeah. Let's be strict. They put in the file source file dest. Seems correct. I hope it didn't swap it. If I did, I would be doomed. Source dest. Let's just do this. Source dest product. Let's just use the same test case again. Okay, I still have it in here, thankfully, just for fastening this up. Spend a lot more debugging rather than constructing the algorithm on its own. I should put a slash in over here so I can see it. I spend a lot more time debugging. That's a good program. That's a good program. That's a good habit. Spend a lot more time debugging rather than programming, because debugging is important. 1 3 is 0. 1 2 is 1. 2 4 is 0. Of course, it's not in there. 2 4 is 0. 2 3 is 2. 1 4 is 3. Oh. How did it get to 3? How did it get to 3? I only added twice. Oh, because the source area. I should break this to prevent addition. I think that's the issue, yeah. Yeah, I think that's the issue. I didn't break it. I forgot to break it. Oh. Because once you compare, you don't need to compare it anymore. Gee. See, so nothing it's more than 2. 2 3 is 2. 1 4 is also 2. What does this say? 1 3 1 2 2 3 is somehow 2. 2 is already there. 3 is already there. They take 2 3 or take 2 3. I think 2 3 4 2 4 4. 2 3 4 and 2 4 4. Oh, right. Yeah, I see now. Because that doesn't want to. Yeah, I guess that's the issue here. I'm trying to think what's the best course of action. Everything talks one less node. 2 3 4 is not taken somehow. Because I guess in the algorithm there's a, wait, is that like that? Is it like that? 2 3 4 is, should it be taken? Should it be taken? Should it be taken or not? 2 3 kind of god. 2 3 2 2 3 2. Ah, yeah, of course. 2 3 2 should not be taken. Should be taken because actually no. Does it? Is it taken? Should it be taken? I think it should be. Should it be taken? 2, 3, yeah, because or is it not? No, yeah, 2, 3 should be taken. 2, 3 should be taken or not. I do not know. Two, 4 is 0. 2, 3 is 2. 1, 4 is definitely not taken. 2, 3 should not be taken too. Okay, I'm just gonna look at for. Okay, I'm gonna look for Kruskal algorithm stuff. And I'll be right. Hold on.